Hello, my name is Joseph Balderas, and today I'm going to be talking about a deterministic variant of maximum posterior manifold embedding. In data analysis, dimensionality reduction is a central topic which focuses on reducing high-dimensional data to a lower dimensional space so its structure can be better understood. Of the countless dimensionality reduction techniques available, the T-distributed stochastic neighborhood embedding, or t-SNE algorithm, is especially popular for visualizing high-dimensional data. The goal of our research is to use the t-SNE algorithm to help develop a deterministic variant of maximum posterior manifold embedding, or MPME. MPME is a probabilistic framework which uses a prior distribution to model a posterior distribution for data in a lower dimensional space with the aim of uncovering the skeleton structure of the data. We test if this new model can improve the performance of the t-SNE algorithm. Say we're given data points x1 through xn, where xi lives in R(D). Let y1 through yn be the corresponding embedded data points living in the low dimensional space. We want to estimate the density function p of y given the data d. And if we have a prior distribution pi of y, then MPME aims to solve the optimization problem given in equation 1. So the density p can be challenging to estimate for general priors pi. Thus, we convert the problem to a deterministic problem. For our proposed model, we will replace the KL divergence in equation 1 with the objective function of the t-SNE algorithm given in equation 2. So the final optimization problem we want to solve is given in equation 7. So in equation 7, we have a term that is preserving pairwise distances over all the points. But this is potentially too strict of a constraint. So we're going to consider the relaxed problem given in equation 8. So now we only want to preserve pairwise distances over neighborhood pairs. Problem 8 can be solved via subgradient methods. And the subgradient of that objective function is given in equation 11. So now we can go through the subgradient method outlined in algorithm 1. So we have observed data D and all of our parameters. We want to calculate the distance matrix, compute the P sub ij's as done in t-SNE, and we want to use t-SNE to initialize our embedded data. Then we want to construct the K-NN graph and A as defined in equation 9. So for k equals 1 to n, we're going to perform subgradient descent. So there are some additional modifications to algorithm 1 that we want to make. So after testing algorithm 1, we observed that the new method was unable to exceed the performance of the t-SNE algorithm. This promoted us to use a supervised learning approach in the construction of the K-NN graphs n sub I. So if we have data with labels C1 through Cn, then we can restrict the K-NN graphs to only contain points having the same labels. An additional measure we take to improve the performance of algorithm 1 is changing the squared Euclidean distance matrix for the original data. Instead, we can run algorithm 1 substituting the Euclidean distance matrix with the normed distance matrix. So that's the Euclidean distance matrix, but we divide each entry by the maximum entry. We can also use the cosine distance matrix, which has entries given by phi sub ij. So now we can talk about the numerical experiments. So we test algorithm 1 against t-SNE on 4 data sets: the MNIST dataset, the image segmentation dataset, the PIMA dataset, and the Olivetti faces dataset. And those datasets are summarized in the table. So as a performance metric, we use the K-NN test with the 70-30 training split. We abbreviate algorithm 1 by alg1, algorithm 1 with normalized distance matrix as alg1n, and algorithm 1 with cosine distance matrix as alg1c. So the most notable results from our experiments are the high performance by alg1n and alg1c. As can be seen from the charts above, these two methods outperform t-SNE and alg1 on the MNIST image segmentation and PIMA datasets. We suspect the high performance by alg1n and alg1c is partially attributed to overfitting and would like to verify this guess by repeating the experiments again with much smaller training sizes. For future work, it may be beneficial to explore additional loss terms that depend on mid-near points and far points. Thank you.